In this video, we're going to take a look at sketching the derivative of a function. So this process helps to usually fill in some of the conceptual gaps that we might have when we're just looking at the equations of functions and their derivatives. So we're just going to take a look at a few examples here, and you'll just have to do some more practicing, and hopefully this will help some of your conceptual understanding of what a rate of change is and what a slope is. So a couple things to remember. The derivative represents slope. Okay, so therefore the slope values on these graphs are going to be plotted on our derivative, on our f prime graph. Okay, so starting off with a basic example here, these are just line segments, and we know on a line the slope remains constant. Okay, so as I'm looking here, from the x values of -4 to -1, this line has a constant slope of 1. There it is, right up 1 over 1. So over here, I'm going to graph the slope values of +1 between the x values of -4 and -1. So here's how that looks. From -4 to -1, I'm going to plot the slope values of a constant 1. Okay, so we know that, just to save some time here, we're going to graph just that horizontal line. Notice this next part of the segment here. This goes between -1 and 1 for x. And look at this slope here, down 3 over 1. This is a constant slope of -3. So over here, between -1 and +1, I'm going to graph a constant -3. And over here, this last line segment has a slope of 2/3. So from the x value of 1 to 4, I'm going to plot a constant slope of 2/3. So here's 1, just a little lower than that. So here's about 2/3. Okay, so that's just the basic idea of what we're doing here. Remember that f prime is the slope of this. So we're just taking all these slope values and plotting them here. Okay, so for the rest of these, I might suggest you pausing the video here, and these are just some suggested guidelines that I might suggest for you to use when you're working through these. So pause it for a minute, copy these down, and we'll continue. Okay, so with these guidelines, and I'll talk you through them here, here's our next example. Okay, so the graph of f, and we're going to be graphing f prime over here. Suggested guideline 1 says identify the values where the slope is 0. So we're looking for horizontal tangent lines, and I see one right here, and it looks like right about at when x is -1, that's going to be a horizontal tangent line or a slope of 0. And then again, let's just make it easy on ourselves. I know you could argue it's a little over there, but we're going to say at +1, there's a horizontal tangent line there. And in those guidelines, those are x-intercepts. Think about it. The slope there is 0. The function value on the x-intercept on the x-axis is 0. Above is positive function values, below is negative. So we're going to have x-intercepts here and here. Next thing we need to identify, based on the guidelines, areas where the slope is positive or negative. And that's going to be either graphing above or below the x-axis. So right here, until we get to this point right here, these are positive slopes. Pretty steep here, maybe 4 or 5 for a slope. Maybe a slope right here of about 1, and then here's 0. So over here, this point between like -3 and -2, those are going to be graphed above the x-axis. Notice here though, these are negative slope values, and so between -1 and +1 below the x-axis, and then here again positive slopes. So these are going to be graphed above. All right, the third guideline, and just so you know, you can kind of tell what's going to be happening here, but this third one, it's a little tricky to understand at first, but it helps you identify how this curve is going to fit. So we're going to identify the regions where the slope is either increasing or decreasing. So this is tricky. So here, what I like to do is I like to say some estimated slope values here. So I might say 5, 4, 3, 2, 1, 0. And what did those slope values do? Those slope values decreased 5, 4, 3, 2, 1, 0. So I know my graph up here is going to be decreasing until it gets to that x value of -1. So decreasing. All right, I'm going to... Here, these negative slope values, think about what's happening here. 0, -1/2, let's just say -1 here. What did those values do? 0, -1/2, -1. Those values decreased. But look what happens here. Slope of -1, -1/2, 0. Those increased. So decreasing slopes, increasing slopes. That just means moving down, moving up. And we know we have to hit that point. That's going to be an x-intercept. Here, slope values positive above the x-axis, and these numbers are increasing. 0, 1, 2, 3, 4, 5. So here it is, 0, 1, 2, 3, 4, 5. And we have the graph of our derivative, f prime. In hindsight, you might be able to even say, well, this is a cubic function, and because of my power rule, if I take this down by 1 degree, a cubic function, x cubed, down by 1 degree becomes a quadratic function, x squared. So that's another way to kind of look into the details here. All right, a couple more here. All right, as I look at this one, I do not see any horizontal tangent lines. I don't see any places where the slope is 0. Okay, so we have to skip that first guideline. All right, so we're not going to have any x-intercepts on this one. Guideline 2 says identify the areas where the slope is positive or negative. So let's see. I see negative slope values right here, like -1/2, maybe like -1, and it gets steep here, like -5 maybe. All those are negative slope values, so I know my graph is going to be below the x-axis. Over here, again, negative slope values. So that part's going to be graphed over here as well. All right. Part 3, guideline 3 says, are the slope values increasing or decreasing? So just say some of those numbers, like -1/2, -1, -2, those numbers are decreasing. So here's staying below the x-axis, and my slope values are decreasing. Look here. Once again, negative slope values, and what's happening here? These numbers start like maybe -5, -4, -3, -2, -1, -1/2. These numbers are all increasing. So my graph is moving up on an increasing slope value. All right, so here's the graph of our derivative on that one. And if saying the numbers kind of confuses you, you might not be to this concept yet with the second derivative and concavity, but notice how this opens down. Opening down creates a decrease in the first derivative. Look at this one. It's opening up, so that's going to create an increase. If that helps you, use that. All right, last one here. Slopes of 0. I see a slope of 0 right here at -3. That's going to create an x-intercept at -3. And I see another slope of 0 right here at +3. So that's going to be another x-intercept. Next, negative slope. So that's below the x-axis. Positive slope above the x-axis. Negative slope below the x-axis. Positive slopes above the x-axis. All right, what's happening here? These slope values, -1, -1/2, 0, increasing, increasing. So here we go. Increasing, increasing. What's happening here? These negative slope values, -5, -4, -3, -2, -1, 0, increasing, 0, 1, 2, increasing. So here we go. Increasing, increasing. Kind of tricky one here. Notice this sharp point right here. This is called a point of non-differentiability. We cannot determine the slope of this point right here. In order to determine the slope, there needs to be smooth transitions. This is a sharp transition. We can't tell the slope here because this slope in an instant changes from positive to a negative slope. So the way we handle that is, notice, in an instant, the slope changes from positive, there's an open circle there, in an instant, boom, changes to negative right here. Yeah, I said boom. All right, so there's a little bit of a tricky one there for you. Point of non-differentiability, therefore it is not defined on the first derivative.